As a bustling city wakes up in India, millions of people start their day checking their phones, pouring a glass of water, and stepping out onto their balconies. It feels like a routine morning, but every single one of those mundane actions intersects with massive global scientific research happening right now. Take that morning glass of water. This chart outlines a new machine learning workflow designed to keep it safe. Researchers trained an AI on dozens of past studies to identify the perfect bimetallic catalysts, mixtures of metals like palladium and platinum. The AI predicts exactly which combinations will most efficiently convert toxic nitrates in the water supply into harmless nitrogen gas. Then there's the chore of taking out the trash. Absorbent hygiene products, specifically diapers, generate up to 160 million metric tons of global waste every single year. Most of it ends up piled in landfills or incinerated. To cut down this massive pollution footprint, environmental scientists are proposing three main interventions: developing fully compostable diaper designs, expanding advanced chemical recycling, and pushing for earlier toilet training to simply reduce the total volume used. Stepping out onto the balcony, you might expect your potted plants to offer a buffer against the city smog, but a massive review of over 34,000 research papers found almost zero direct evidence that domestic gardens actually reduce household exposure to dangerous air pollution. The way air flows through a tiny balcony is totally different from a large park, meaning those plants aren't scrubbing the air the way we assume. Our immediate environment, the water from the tap, the trash on the curb, the air in our lungs, is dictated entirely by these micro-scientific interactions, rather than the comforting assumptions we usually rely on. Outside the apartment, the local weather forecast is painting a harsh picture. Climate models project that by the end of the century, small tropical islands and coastal regions will face multi-month stretches of dangerous, humid heat waves. Under high-emission scenarios, the heat index could regularly exceed 46 degrees Celsius, turning rare heat events into annual, lethal threats. Looking at this climate map of the Mediterranean, we can see exactly how reduced atmospheric moisture triggers historical catastrophes. Around 3,200 years ago, severe, overlapping droughts converged over this specific region. This loss of moisture pushed the Bronze Age civilizations past their critical threshold for water availability, resulting in a systemic societal collapse. We are seeing echoes of that instability today. Intense droughts and extreme heat have recently fueled massive wildfires across France, Spain, and Italy, forcing tens of thousands of people to evacuate, as local emergency resources are entirely overwhelmed. But we're also building better defense systems. A new AI framework can now generate highly accurate ensemble precipitation forecasts up to 2 weeks in advance. Meanwhile, researchers are looking at Australia's multi-hazard alert system, which combines incident stage warnings with direct phone alerts, as a blueprint for unified national emergency responses. Surviving the daily reality of extreme weather means abandoning reactive panic. We have to adopt these predictive, AI-driven systems to adapt our infrastructure before the next disaster hits. Fast forward to the midday commute. You open your phone, and your feed is a rapid-fire stream of biological breakthroughs, discoveries that directly impact the human body and our evolutionary history. In just the last few weeks, scientists identified a specific compound that helps aging muscles stay strong. They discovered potential new therapeutic targets to prevent preeclampsia in pregnant women, and tested an experimental plague vaccine that protects mice even when they are missing key immune defenses. This diagram illustrates a massive leap in diagnostics called surface engineering. By coating extracellular vesicles with lanthanide ions, researchers created a super homotypic interaction. This amplifies detection signals 10,000 times, allowing doctors to spot rare cancer cells in complex fluid samples in hours instead of days. And the evolutionary quirks keep coming. Biologists figured out why mammal teeth never evolved to slice and crush equally well at the same time. Ornithologists mapped out how birdsong varies across the globe, tying thousands of species together with just 8 core motifs. And marine biologists found that commercial fishing is actually altering certain fish populations down to the molecular level. We're even digging up our own ancient habits. Using a quantum microscope, archaeologists recently detected hidden microscopic traces of fire use by Neanderthals, perfectly preserved beneath millennia of pale ash. Whether it's engineering a new way to hunt cancer or uncovering an ancient fire pit, human health and evolution are part of one continuous, ongoing biological adaptation. Back out in the physical world, technology is being deployed to aggressively manage our changing environments. Take this small, spider-inspired robotic boat. It's designed to track and rescue people by autonomously navigating treacherous floodwaters where human responders can't safely go. Or consider the GLOW-CO mapping project. Researchers have painstakingly drawn high-resolution digital boundaries around 1,250 vulnerable coastal UNESCO sites, like ancient cave temples located below 20 meters of elevation, to accurately model their risk against rising sea levels and erosion. Offshore, scientists are feeding 20 years of temperature and salinity profiles collected by robotic Argo floats into an AI. This allows them to accurately map the vast, deep-water geostrophic currents of the Atlantic Ocean. We are even testing ways to use the ocean as a giant carbon sink. Early work shows we can convert dissolved CO2 into stable carbon, pulling massive amounts of greenhouse gas from the atmosphere. Protecting coastlines requires moving beyond static seawalls, deploying autonomous AI technology to manage the ocean. It's 2 a.m. You're still staring at your screen. But the deeper you look into the hardware, the more you realize your phone operates entirely on the bizarre, invisible rules of quantum physics. Engineers are using inverse design algorithms to create photonic components, like wavelength splitters and mirrors, that are up to 500 times smaller than conventional designs, packing immensely powerful light-based circuits onto tiny silicon chips. Here, you can actually see the behavior of light at that microscopic scale. By applying an ultra-thin layer of fluorescent quantum dots to a metal surface, physicists captured this fringe pattern, directly imaging the velocity and dispersion of internal plasmon waves. And this graphic tracks the next frontier, a light beam manipulating an atom for quantum computing. Specifically, researchers are testing zinc oxide spin qubits. But as they add more qubits, they run into the quantum Zeno effect, where even weak perturbations from the environment act like a measurement, effectively freezing the computer's state in place. Meanwhile, physicists are bombarding palladium and titanium foils to boost nuclear fusion rates far beyond standard limits. And they are using mathematical frameworks, mapping particle interactions like piano notes, to deduce the existence of heavy, hidden particles at the edges of the standard model. The devices we depend on every single day are bound by subatomic forces that scientists are only just beginning to map, measure, and manipulate. If we zoom all the way out and look up, that active, volatile energy is everywhere. High-resolution simulations show that Venus isn't dormant. It possesses young, steep rift flanks that are actively extending by centimeters a year. Out by Jupiter, simulation suggests the water inside Europa's ice fractures is so turbulent it will make reaching its hidden ocean incredibly difficult. Look deeper into space, and astronomers have just caught a massive galaxy in the process of assembling itself, piece by piece, a mere 1.2 billion years after the Big Bang. And right now, arrays of high-frequency radio telescopes are sweeping entirely new, unexplored submillimeter channels, hunting through the static for alien technosignatures. From the nitrates in a morning glass of water to the hunt for alien signals in deep space, science operates as the invisible framework governing every layer of our reality.